All right, so picking up where we left off, technical difficulties. Remember, we were trying to find the length of each of our rectangles, and we do that by plugging each of those x values into the function to figure out exactly how long they're going to be. Because in order to actually find this length, you would essentially are trying to figure out, okay, what's that point on the actual function, because that's going to correspond to the length. So you'll have to do f of 0 for that thin strip of a rectangle. You'll have to do f of 1/4 for that second rectangle, f of 1/2 for the third rectangle, and then f of 3/4 for that fourth rectangle. So when you do that, f of 0 is what? 0. F of 1/4? 1/16. F of 1/2? 1/4. And f of 3/4? 9/16. And so to find the area of all of the lower rectangles, you would have to multiply your length by your width of each of the rectangles, and then of course add them together. So then that's going to be 1/4 times 0, 1/4 times 1/16, plus 1/4 times 1/4, plus 1/4 times 9/16. What I could have also done is I could have done 1/4 times the sum of all those values, because essentially that's the same thing. Probably would have been a little easier too. But I want to make sure everybody sees that I'm multiplying each width by each length. Didn't want to confuse anyone. And so hopefully you ended up with 0.219 when you round to 3 significant figures, or 7/32, which was the exact area. Questions?
The values that you plugged in for the length for x, are those the ones that you found like on the graph?
Yes. So 0, 1/16, 1/4, 9/16 are exactly those points that correspond to like that respective y value for that x value. And
so like for the last one, that orange line is 3/4. Like that's the length of it?
No, so 3/4 is the location of the, like that's the x coordinate, and then 9/16 is the y coordinate. And that y coordinate is that vertical distance from the x-axis to that point on the curve. So essentially we want the y coordinates of each of those corresponding x's, because those are going to be the lengths of our rectangles.
So this is only an approximation, right? Because we didn't like count those little triangles like above the rectangles.
Correct.
Okay.
That's correct. This is an approximation, an estimate. Okay. Now we can actually do the exact same thing except for the upper rectangles. Okay, we can do the exact same thing for our upper rectangles. And again, the reason why they're upper rectangles is because the height of each of those rectangles is the upper value of the function at the endpoints of the subinterval. Okay? So this time, we're using these respective values. That's 1/4, 1/2, 3/4, and 1 this time. Okay? Because we wouldn't use 0 because at 0, that's not the upper endpoint of a rectangle. Okay? So again, we have 4 rectangles. Remember, this was 4 subdivisions. Okay? We have all the widths that are equal. We just need to find their corresponding lengths. So again, finding this, 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 and this. So we have a small rectangle, the next one up, the next one after that, and then we got that super tall one. Each one of them has a width of 1/4, just like before. Their lengths we find by doing what?
Bring the x to the function.
Plugging the x into the function. So this time my x's are 1/4 for that first rectangle, 1/2 for the second, 3/4 for the third, and then 1 for the fourth one. And from the last time that we did it, we know that 1/4 squared is 1 over, and we know that, and we know that 1/2 squared is
1 over, no, 1
1
over
over
4.
16. Wait.
1 over 4.
1 over 4.
4,
3/4 squared,
9 over 16.
and then 1 squared is
1.
1. All right? And so again, we are trying to find the area of the upper rectangles. And again, area is equal to length times width. So we're going to multiply each of our lengths by each of our widths. And we are going to add them up together.
I got 0.46875.
So 0.46875. So that'd be 0.469. Okay. So then the area of the upper rectangles would be 0.469. So what does this mean? What does this mean for the area underneath my curve of x squared from 0 to 1? What does this mean? Well, first off, as we can see, from 0 to 1, the function is increasing the entire time. So if the function is going to be increasing the entire time, or even decreasing the entire time, then we know that the lower rectangle area will always be less than the area of the upper rectangles, if it's an increasing function the entire time or a decreasing function. If that is the case, then the area underneath the curve of our particular function, which is x squared, from 0 to 1, is going to lie in between these two areas, the area of my lower rectangles and the area of my upper rectangles. Okay? It's going to lie somewhere in between those two numbers. That's what this inequality here, this compound inequality represents. The area of my lower rectangles, and then the area of my upper rectangles is actually going to encompass what the actual area is of the function between 0 and 1. So again, just to make sure, by finding the area of the lower rectangles and the area of the upper rectangles, we're able to basically say that the exact area of our function x squared from 0 to 1 is going to lie between 0.219 and 0.469. Now also realize we only did 4 subintervals, okay? The more subintervals that you create, the more exact your area is going to be, okay? We only did 4. What if I asked you to do 8, 16, 50, 100, more than that? The more rectangles you have, basically that space that Michaela had pointed out that was in between those rectangles is going to continue to get smaller and smaller, okay? And then that space for your upper rectangles is going to continue to get smaller and smaller and smaller the more rectangles that you have, okay? So what I'm going to have on this next slide is the area if you created 8 subintervals, okay? If you created 8 subintervals, and you don't have to write this down, unless you want to write it down later, do that later. Your width now becomes 1/8, not 1/4, okay? And then of course, this is how from 0 to 1, those x values would break down for your lower rectangles and the x value for your upper rectangles. Of course, you plug each of those values into the function. You will multiply them by the respective widths. And then the area of your lower rectangles would be 0.27344. And then the area for your upper rectangles will be 0.39844. So by adding in more subintervals, the area actually is going to lie not between 0.219 and 0.469. It's actually going to lie in between a smaller interval. So the more subintervals you have, the more rectangles you have, the closer you're getting to your actual area. Does that make sense?
Yes, ma'am.
Wait, can you go back to what was the first one?
So the first one was between 0.219 and 0.469, but that's just with 4. So then when you double your number of rectangles, now it's essentially went from being wide out here to being pushed in more. So just imagine if we did 16 subintervals, it'd be even closer. 32 would be even closer, okay? So again, the more subintervals you have, the closer you are to your area being more accurate, okay? And again, it's going to start to converge to a particular value, which is the actual exact area underneath your curve. Now, of course, there is an easier way to do this, okay? Of course, there's an easier way to do this because the more subintervals you have, you're not going to sit there and plug in 1/8, 2/8, 3/8, 4/8, 5/8, and so on and so forth, especially if you have a lot of subintervals. So what we can do is we can actually use our calculator to actually let it produce the numbers for us, like that f of 1/4 and that f of 1/2 and so on and so forth, okay? So to do this, hopefully everybody has their calculator out. You want to press the math button, and then you want to press the 0 button. And what should pop up is your sigma notation, okay? Like that empty template back from sequences and series, okay? We're going to use this to essentially find the sum of all of those areas. You just have to make sure you type in what you want the calculator to find. Here, into this very first box where your blinker should be flashing, you want to put in X. Okay, everybody knows what the X button is, right? All right. Now we are going to have to do this twice, one for your lower rectangles, one for your upper rectangles, okay? All of your lower rectangles are going to start at that first X value, okay? Which was 0, okay? So we'll do the lower first. I'll do the lower in orange and I'll change the color to do the upper. So we're going to type in 0, okay? That was the X value of that lower one, okay? And then on top of the sigma, for our lower rectangles, I'm going to do 3. Because essentially, I have your 0 rectangle, your 1 rectangle, your 2nd rectangle, your 3rd rectangle that represented this. So you have, essentially that's what you're using there, okay? To represent the 1st, 2nd, 3rd X value. And then inside, beside the sigma, this is where you're actually going to type in the function, okay? The expression for which we're going to go about finding your area, okay? Remember, your area was length times width. Your widths were always, it was 1/4 when we had 4 intervals. It was what when we had 8? It was 1/8. So depending on however many rectangles you have, how many sub intervals you're going to have, it is going to be 1/n, okay, in general. Yes?
So like generally whenever you, the place where you put lower 0, is that the starting X point, and then the place where you put forward 3 is the ending X point.
So this will represent our width. And then to represent our length, remember we got that by plugging it into our function. For this particular example, what was our function?
Y equals X squared.
It was X squared. So we're gonna need to put in X squared, but remember, since we were plugging in each one of these sub-intervals, it technically was like 1/4 squared and 1/2 squared and whatever the other values were squared. So we essentially have took that function and divided it into fourths or into eighths. So in general, it's going to be X over N squared to take the entire function and divide it into fourths or eighths or however many. So for our example, we will want to type in 1/4 because we have 4 subintervals, X over 4 squared, which will represent our width times our length. So let's type that in. Oh, this is too big. Math 0, X. I'm doing my lower rectangle, so that's going to be 0. The top number is going to be 3. Then I'm going to type in my function. I'm going to use that fraction feature that I have. And again, I'm using 4 because we did 4 subintervals. We did 4 subintervals by hand. Pretty much is going to check. We're going to do it again also for 8 as well. Okay? So now that I have everything in there, okay? 7/32. That was the exact version of 0.219. I'm going to do the exact same thing to get my upper rectangles. So again, that's math, option 0. Remember, in that very first box, I'm going to put my variable X. And now for my upper, I'm not going to use 0. I'm going to use 1. Okay? I'm going to use 1 for my upper. The reason why is because now I'm starting here at this point, which corresponds to 1. Okay? So I'm going to use 1, 2, 3, and then my top bound is going to be what number? 4. So 1, 4. And I'm going to use the exact same function. 1/4. And then, oh crap. Just ignore me. Hopefully y'all already done this. $15/32, is that 0.469? Okay, so boom, we can use this feature. Going to be very helpful if we have to increase the number of subintervals that we do. Okay, going to increase the number of subintervals that we do. And what we can actually do as well, instead of saying like, okay, well, this is the range between using these lower areas and these upper areas, that's the range. But we can actually kind of get a better estimate of what could potentially be our area by taking the average of the two, right? Because if I can find the average of the two, then basically I'm finding that middle point between those lower rectangles and those upper rectangles. So we'll do the average. That's going to be what was that number? It was 0.218. Okay. Come on. It's not working with me today. So I'm going to take those two numbers, the upper and the lower, and then I'm going to divide them by 2 to actually say, well, a good estimate of what the area is from 0 to 1 of x squared is going to be 11 over 32, or 0.344. Okay, that would be your estimate for the area from 0 to 1 of x squared. And of course, the more subintervals you do, the more rectangles you do, the more exact you're going to be to the area underneath that curve. So if I wanted to do 8 subintervals, okay? I'm going to go to math, option 0. What am I going to put in that first box? X. What am I going to put beside the X? 0, because I'm looking for my lower rectangles first. And if I'm using 8 subintervals, what's going to be my upper, what's going to go on top of my sigma? It's going to be 7. 1 less. It's always 1 less than the number of subintervals that you have. I'm doing the exact same function. Okay, I'm doing 1 over n, then x over n squared. But this time, instead of being 1/4, it's going to be what? It's going to be 1/8, because I'm doing 8 subintervals. So that's 1/8 times x over 8 squared. So as you continue to increase your number of subintervals, you want to make sure you change that n. N represents your number of subintervals, your number of rectangles. So there is my lower area. Now I want to do my upper area. If I'm doing the upper, what goes beside the x? And what goes on top of the sigma? 8. And then I'm going to type that function in again. By doing this, the calculator is going to be doing all of the multiplying of each width and each length and adding them up together. I just need to make sure that I type it in correctly so that the calculator knows that I'm doing the right number of subintervals, and it knows that I'm looking for either the upper areas or the lower areas. You guys do this? So then again, this is the range from whatever 35 over 128 is to 51 over 128. It's going to be those same decimals that were on that other slide with the math already worked out for you. Okay? But if I want to figure out a good estimate of the area underneath the curve, then I want to find the average between the upper and lower rectangles. So I add them up, divide by 2, and as you can see, that's different from when we did 4. When we did 4 subintervals, it was 0.344. But now with 8, I'm at 0.336. So again, the more rectangles you have, the smaller that window is getting, and the closer you're getting to what the actual area is underneath the curve.
So the equation that we've been doing in our calculator, is that to find the area?
That's to find, yes. So the whole sigma part, that's how we find the areas of all of the rectangles. We just have to make sure that we tell the calculator if I'm looking for the lower ones by starting at 0, going to 1 less, or the upper by starting at 1 and going to n.
Miss Anderson,
Yes.
I just want to make sure on the space underneath the sigma, when you write either x equals 1, that means that the last rectangle ends at 1. Like, I don't understand.
Yes. So what this 0 and 1 means is essentially where you're starting from. Okay. So let me erase this. So remember when we had those 4 rectangles in there, okay, and we did our lower ones. Remember, this is where it went from 0 to 1. We divided it into those 4 subintervals. This was our first rectangle. This was our second. This was our third, and then this one was our fourth. This 1 or that 0 for lower essentially shows you where you start. Okay, this is my starting point for that lower rectangle. Then there's my starting point for my next one, the one after that, and so on and so forth. So that's why we go from 0 to 3, because we are representing those lower points along the curve. But for upper, the reason why I start with 1 is because, again, when I split this up into those not the best drawing, but y'all getting my drift here, okay? To represent those upper points, I'm not starting at 0, I'm starting at that very first value to represent this particular x value. So that's why we use 1, followed by 2, followed by 3, and then ending with 4. So don't think of it as these are the respective x values that are on the curve. It's more so of where are my rectangles starting that I'm trying to find the areas of, whether lower or upper.
So whenever we say area, is that the area of each rectangle? Or is it the area?
The area, with the way that I'm saying area, like in this sense, the sigma is the sum of all of the lower rectangle areas or all of the upper rectangle areas. So it's all 4 of these added up together. That's the area. Like when we found those 2 individual numbers, we were finding the sum of all the areas. When we added the lower and the upper and divided by 2, we were finding the best estimate for the area underneath the curve from 0 to 1. So we have the by hand method, which is how we can do it for maybe only 4 subintervals or maybe 3 subintervals, a smaller number. But as the subintervals and or the number of rectangles continues to increase, we probably want to definitely use technology to do so, okay? What's on this slide right here is if we were to continue to increase the number of subintervals, okay? Don't write this down, just take a look, okay? When we did 4 subintervals, this is what we got for the area of the lower rectangles. This is the area that we got for the upper rectangles when we add them all together. When we found the average, we got this number. We did it also using technology with 8 subintervals. We got this for our area for the lower, then that for the upper, add them together to get our average. And as you can see, as the number of rectangles, subintervals increases, the range of the lower areas and the upper areas are getting smaller. Does everybody see how that interval is getting smaller and smaller? It's getting closer and closer to one particular number. Look at the averages. The averages are continuing to get closer and closer and closer to what number? What's 0.33333333333? 1/3. So by continuing to increase your number of rectangles and then finding the average between your lower and upper areas, you will converge to a particular number. So the area underneath the curve of x squared from 0 to 1 is 1/3. Question?
Is there a way to find out how many like subsections you need?
Is there a way to find how many subsections you need? The thing is that there's infinitely many rectangles that can go underneath a curve and above the curve. So if you're trying to get a good estimate or close to, you want to aim for a large number of subintervals, like 100 or 1,000 or 10,000. Now, the types of questions that could be asked of you on the IB exam is they could say, estimate the area using 5 subintervals. And so then you specifically have to estimate it based off of the fact they told you to use 5. And then, so you would find the lower areas, the upper areas, and then find the average between the two. Okay? All right. So let's give it a try. I want you guys to try this next example on your own. Okay? Give you a simple function, y equals x. Okay? And we are going to consider that function, y equals x, and we're going to try to find the area between 0 and 1. Let's divide the interval into 5 subintervals of equal width, and then estimate the area for the lower rectangles and the upper rectangles. Okay? So do A. I just want you to do A using the method that we did for x squared, 4 subintervals from 0 to 1, but this time you're using 5. So we're dividing these into 5 subintervals of equal width, okay? You're doing the lower rectangles and the upper rectangles, okay? So you're splitting this into 1, 2, 3, 4, 5 subintervals, and you're doing all of the lowers. Okay? Did anybody use the formula or did we use our calculator? Calculator? Formula? Okay, well if you use the formula to estimate the area, then you knew that you were gonna have a width of 1/5, and then you would have had to plug each one of these x values into your function, which would have been 1/5, 2/5, 3/5, and 4/5, okay? And then also 0, okay? You can do that by adding all those values and then multiplying it by the width, or you can multiply each width individually to each of the lengths to get your upper value. Your lower value. Similarly, to find the upper rectangles, all right, that's all of these points. Your width is still 1/5, and this time it's going to be 1/5 plus 2/5 plus 3/5 plus 4/5 plus 1. This is if you use the formula. If you used your calculator or your lower rectangles, you should have had x equals, and then on the top, then what would your function have been?
1/5 times x over 5 squared.
You wouldn't square it because your function is just the normal x. So it would just need to have been x over 5. Just x over 5. So then for your upper, you would have had x equaled what number?
1.
And then all the way up to?
5.
And then it'll be the exact same function. Okay? Remember, you want your width times your length when you're creating that function. And so that x over the number of subintervals represents you taking your function and dividing it up into that many subintervals. But either way you do it, whether you do it in the blue and the orange, or if you did it in your calculator, which is the black, you should end up with the same values.
I have a question.
Question.
For the number, like where you have the 4,
Mm-hmm.
for the lower, is it always n minus 1? And then for the upper, it's always equal to n?
Mm-hmm. So what do we get for the lower rectangle areas?
Lower, I get 2, 5, 2 fifths.
So 0.4, 2/5. Okay. That should be the same thing you got when you did it using your calculator. What about the upper? So 0.6. There we go. Okay. So that's the area of your lower rectangles. That's the area of your upper rectangles. So if I wanted to find an estimate for the area, I would take the 2, add them together, and divide by 2. What is that? 0.5. Now, when we look at part B was asking us to actually calculate the area of this function, okay? We're calculating the area of the shaded region. That shaded region is nothing but a what? What shape is that?
Triangle.
Triangle. And what's the old school formula for the area of a triangle? Old school. 1/2 base times height. What's the length of the base? 1. What's the length of the height? 1. So what's half of 1 times 1? So in actuality, we were actually able to get the area underneath the curve and the x-axis bounded between 0 and 1 by using 5 subintervals and finding their averages. It is the area of that shaded region is the average of the upper and lower rectangle areas. Now keep going. For functions that are increasing or decreasing on the entire interval, I mentioned that before we did the calculator way, this process will guarantee that you will find the actual area, okay, underneath a curve using upper and lower rectangles. It guarantees it if it's increasing on the entire interval. However, when it doesn't increase the entire time or decrease the entire time, say there's a turning point along the curve, then you cannot use this method, okay? We were able to use the lower and upper rectangle method because from 0 to 1 of x squared, it was increasing the entire time. And from 0 to 1 of y equals x was increasing the entire time. If it was decreasing, we could have done it too. But if it turns at any point, we can't use this method. A more efficient way for those types of problems that have like a turn, we want to use trapezoids instead. You want to use trapezoids instead. By doing this, we use the average of the values of the functions at the left and the right endpoints. The value calculated will lie in between the area of the lower and then the upper rectangles by using the trapezoids instead of just rectangles. This generally is a better approximation to find the actual area. Because truth be told, if you're not dealing with a curve that's increasing the entire time or decreasing the entire time, which a lot of functions aren't, the trapezoid method is going to be a more, a better approximation, more efficient way. This particular this particular formula is in your reference book. Okay, it is in your reference book. So let's talk about this. This is called the trapezoid rule. All right, it's called the trapezoid rule. What is the area of a trapezoid? What's that formula? Crickets. Cool. All right. Reference book is there. It is there. All right. So our area is 1/2 A plus B. A and B representing the parallel bases of the trapezoid times your height, H. And so what the trapezoid rule does is it takes this formula and it basically rewrites H in terms of A and B. Okay, so H is found by doing B minus A over N. Okay, A and B essentially represent your starting and your ending X values. And N represents your number of trapezoids that you're going to use to approximate the area. Okay, so H is going to be B minus A divided by N. B is that ending point, A is that starting point, divided by your number of trapezoids. All right, we are also going to need this little bit down here at the bottom. This is X sub I, so a subscript of I is equal to A plus I times H. A is the same A, the value that we start with. I is 0, 1, 2, so on and so forth, all the way up to N. In other words, like your starting line all the way up to your ending line, so essentially like your number of trapezoids. And then H is the same H from the formula B minus A over N. In other words, get all these formulas down, please. So in that way I can show you how to use them. So
What was xi equal to?
xi is equal to A plus I times H. So the area for the ith subinterval of the shaded trapezoid below. Okay, so here's a function. You see the trapezoid is given by this formula. This is the same formula that is in your reference booklet. And this is what you use to approximate the area of the area underneath a curve. H represents that formula from the other slide, B minus A over N. Y sub 0 represents your function when you plug 0 in for X. Okay, so Y essentially represents your function. So Y sub N would be, your last trapezoid, that numerical value plugged into your function. And all of this part that's beside that 2 parentheses represents everything in between. One thing that I want to make sure that to highlight is the fact that all of this is in parentheses. So you basically perform the addition and then you'll multiply by 1/2 times H. Don't forget about that, okay? Definitely want to highlight that because when I was going through and doing the example problems, I kept messing up and I was like, what's the issue? And I was missing that extra set of parentheses. So we're going to use this formula and we're going to look at 2 examples. I don't know how far we'll be able to get because we're kind of running out of time, but we're going to continue to practice this, more on Thursday. So I just copy the formula over, it's up there. Yeah, I'm gonna highlight this so I don't forget. Okay, and here's the example. We're gonna use the trapezoidal rule with 6 subintervals to estimate the area between that function, the square root of 6 minus x squared, the x-axis, and the x value from 1 to 2. Of course, if you wanted to graph this and see what it looked like, you could get you could do that. You can see the general idea of what it looks like. The function kind of looks like this, okay? And so since we're looking from 1 to 2, we are basically trying to find this area right here. That's what we're trying to find, okay? And we're going to use trapezoids, 6 of them, to estimate this area. And as you can see, it kind of, because it curves in that particular way, a trapezoid is going to be the better approximation. Because if anything, it kind of looks like a trapezoid, doesn't it? Yeah. Okay. Just minus the, there's like a little bit of gap and stuff like that. But we're going to split this into 6 subintervals. Okay. So let's pull out all the information that we need. Let's pull out all the information that we need. If I'm doing 6 subintervals, that means that n is equal to 6. Okay? I'm going from 1 to 2. So 1 is my A value, and 2 is my B value. That's where I'm starting, that's where I'm ending. So since I have that information, I can find out the value of H, which is the formula B minus A over N. So that's going to be 2 minus 1 over 6, or just 1/6. And then I need my X sub i's, okay? My X sub I. That was the formula A plus I times H. Well, as I can see, A is 1. H, I just found out to be 1/6. And so then it's just going to be 1 plus 1/6 I. Because remember, I is going to start at 0 and go all the way up to N. So I is going to be 0, 1, 2, 3, 4, 5, and 6. So it's from 0 to N. So remember, we're splitting it into 6 subintervals between 1 and 2. And so now essentially what I need to find is I need to find my y sub 0, my y sub 1, my y sub 2, y sub 3, y sub 4, y sub 5, y sub 6. Okay. All right. So to make this as clean as possible, I'm going to make a table. The table, all that's going to do is just going to make all my work just nice and organized, nice and neat for us to look at. Y'all know me, I can go everywhere. All right. I do need to look at all of my i's. I'm starting at 0 and I'm going all the way up to 6 because I'm doing 6 subintervals. I need my x sub i's, which are essentially for every I value, I'm plugging it into this formula. And the reason why I need that is because those x sub i's are what's going to go into my function to represent y1, y2, y3, y4, so on and so forth. Okay? So when I plug 0 into 1 plus 1/6 I, I'm going to get 1. When I plug 2 in, I'm going to get 1 and 2/6, which is, I'm sorry, 1 and 1/6, which is 7/6. When I plug 2 in, I'll get 1 and 2/6, which is 8/6. Yes, I know that can be reduced, but I'm not going to. I'm just going to leave it as 8/6. When I plug in 3, that's going to give me 9/6. See why I left it this way? When I plug in 4, I get 10/6, 5/6, 11/6, and then when I plug in 6, I'm going to get 2. That is how those are like the respective x values when you split this into 6 subintervals. Now I need to find the corresponding y's when I plug each of those x values into my function. Okay, find each of those y values. So I need to plug 1 in for x into the square root of 6 minus x squared. I need to plug 7/6 in, 8/6 in, 9/6, all of them in for x into my function. Can you guys do that for me very quickly? So when we plug the x sub I values into the function, we get those respective results. Now, of course, these are rounded. Y'all already know how I feel about rounding. Y'all already know how I feel about decimals, okay? But remember, this is an estimate of the area. And considering that I'm gonna be adding these values up together, multiplying them, and then rounding my final answer, by providing a few more decimal places, I'm able to at least still stay kind of true to what the area is if I were to use the exact values. Yes, there is a way to use the exact values to get the exact area from 1 to 2 of that function. But remember, we're estimating right now. So I need to take all these values and plug them into my formula. I'm going to do that in purple right here. So it's going to be 1/2 times h, which is 1/6. Then I'm going to multiply y sub 0 plus y sub n. Well, y sub 0 is my first value, y sub n is my last value. So I'm going to take that 2.2361 number and add it to 1.4142 number. Then plus 2 times the sum of all of the other values in between. So I need to do y1 plus y2 plus y3 plus y4 plus y5. I need to add up all of those numbers in the middle because they're going to get multiplied by 2. And when I perform this, when I do this, I will get an estimate for the area from 1 to 2. This I'm going to round to 3 significant figures. The area is 1.90. This, of course, is how you use the formula by hand, okay? Plugging it in, using all the formulas, et cetera, et cetera. Yes, you can produce this table by using your calculator. It will make the mathematical process go about a lot quicker, okay? And then it'll be readily available for you. So how do you do that? How do you get that table, that information? You'll still have to find H, you'll still have to find like the actual area itself, but at least to help you out with the table part, we want to use the table feature in our calculator. Press stat, then press enter, okay? Because then you'll take you into your list, your L1 and L2. Hopefully we haven't forgotten that from stats, okay? In L1, you want to type in all of your I values, okay? Essentially, we're going to create the table that we created over there. So you want to type in all of your I values. That's 0, 1, 2, 3, 4, 5, 6. Remember, you start at 0, you go all the way up to N. Then in L2, what you want to do, once you type it all in, you want to go over to your L2, like actual L2, the title, and you want to type in the function that represents X sub I. So at L2, you want to type in the function that represents X sub I. That was 1 plus 1 over 6 I. All of your I's are located in L1, so you want to do L1. So 1 plus 1/6 L1. I'll do that on mine so you guys can see. Stat, enter. All of my I's in L1. And then when I go over to L2, I want to actually go up to L2 and I want to type in that function, 1 plus 1/6 L1, because it was technically 1 plus 1/6 I. Well, I'm trying to do it for the entire table. So I'm going to do second 1. So it does 1/6 of all of my I values and then add 1 to it. And boom, there are all the values. Does it for me.
What did you say you pressed to get
Second 1. Then in L3, we want to type in our actual function. So we're going to go up to L3 and we want to actually type in our function. Well, remember, our function was the square root of 6 minus x squared. All of my x's are sitting in L2. So I want to do L2 squared. So the calculator knows, do 6 minus that corresponding x value, square it, and then do the square root of it. So in L3, with L3 highlighted, I'm going to type in the function. That's the square root, 6 minus L2. I get L2 by doing second 2, and then I'm going to square it because the lower the x's are being squared. Weren't those all the values you guys came up with when you did it by hand? There you go. So then by having this table here, you're able to just go straight into plugging it into the formula, okay? It save you a few minutes. This is the trapezoidal rule, okay? This is one of the newer concepts that they added to the curriculum when they changed things over. So you definitely want to make sure that you guys have this. Now, we are basically at the end of the period, but this is what I do want you guys to do tonight for homework. I want you to go back through and I want you to look at your notes. Make sure you understand the formulas for the upper rectangles and the lower rectangles. Make sure you understand trapezoidal rule, and I actually want you to try to do trapezoidal rule with this problem. I will screenshot it and I'll put it in your folder, okay? And this will be the first thing that we go over on Thursday, all right? You can use your calculator, or if you feel more comfortable doing it by hand, that's up to you, okay? But I would like you to try both so you can get comfortable with both. So just to recap what we've talked about today, we are now in integration. Integration is the reverse process of differentiation, what we did with derivatives. It allows you to find the area underneath the curve. This can be done using your rectangular method by finding your lower rectangles, finding your upper rectangle, areas I mean, and then finding the average between the two to get an estimate. The more rectangles that you have, the closer you'll be to the exact value. The rectangular method only works for curves that are increasing on the entire interval or decreasing. When they're not, that's when we use the trapezoidal rule, which is what we just went over, okay? The respective formulas for the trapezoidal rule, you'll need these, of course, and then the actual formula that is in your reference booklet, okay? We did go over how to do it in our calculator. So if you need to refresh your memory what to click on your calculator, rewatch the video, and then of course bring your questions to class on Thursday.